Okay, so I forgot to mention it again, but there was a simulation from O-Physics for looking at a mirror, and it's also a really good resource for helping you see how mirrors work. So, anyhow, hopefully you've been sketching out the P ray, the C ray, and the F ray, and so that is a good practice for seeing how mirrors work, and you really ought to do it at least once. Okay, so now that you've been able to sketch it out, we want to use these kinds of ray diagrams, and we want to think about this a little more quantitatively. So in the figure above, we have a red arrow that is pointing up for our object, and it is placed beyond the center point. And the height of the arrow we will define as the height of the object, and the distance from the mirror to the object is the distance of the object. The distance here is positive because our object is on the side of the mirror where the light is. And suppose we have drawn our C ray, our P ray, and our F ray, and we have found where the image is located. Like we did last time, the image is upside down, and it's a bit smaller than our original image. Now we will follow a ray of light that travels through the object and bounces off the very center of the mirror. This ray bounces off the center, so the normal line is along the center axis, and the incident angle and the reflected angle are the same. Because the angles are the same, we can then use the similarity of triangles so that the two triangles have the exact same angles. So the second triangle that we're looking at is the triangle that uses the reflected angle, right angle, and the height of the image. The first triangle is the height of the object, the distance of the object, and then that ray that we discussed going from the height to the center of the mirror. So once we've done that, we can use the similarity of triangles, and so what happens is the angles are exactly the same in these two triangles, so that means that the ratios, so the ratio of the height of the object and the distance of the object, is equal to the ratio of the height of the image divided by the distance of the image. So we can rearrange that to get the distance the distance to the image divided by the distance to the object is equal to the negative of the height of the image divided by the height of the object. So in this case, both distances are positive because the images and the object are both on the same side of the mirror. So to show that the mirror is inverted, we use negative because the height is pointing down. Notice that the height of the image divided by the height of the object is the magnification, m. If the height of the object is much larger than the height of the image, then the image looks small, and if the height of the image is larger, then it looks large and is magnified. One thing to focus on a bit is the negative sign. So if the magnification is negative, then the image is inverted, because the height of the image is in the opposite direction of the object itself. If the magnification is positive, then the image is upright, and it's in the same direction as the object. In the case of mirrors, only inverted images can be real, or at least with a single mirror, I should say that. With a single mirror, only inverted images can be real, while upright images with positive magnifications are virtual. So also remember, if you want the focal point, starting from the center of the radius, the focal point is half the radius, and for concave, the focal point is positive because light can cross through the focal point, whereas for convex, the focal point is negative because light can't reach the focal point. All right, I think this is a good place to stop. So for Thursday's class, we're going to start to use the mirror equation to solve for some of these magnifications, and you have a couple more questions to do. All right, so good luck and take care of yourselves.